So today I'm going to talk about what I said, but I would like to call it one-shot object X, where X can be a detection or classification. So as you all aware, we are in the age of big data or big data sets. We have the COCO, Common Object in Context, with 80 categories and hundreds of thousands of images. We have the ImageNet, now with 22,000 categories and millions of images. We have the new Open Images with a huge amount of images and categories and even bounding boxes for them. So it's a detection dataset. We have the YouTube dataset with 450,000 hours of video, which is, a lifetime. And of course, this is very huge for the crowdsourcing companies. So they learn a lot of things, labeling a lot of images. But I would like to argue that in many important applications, you still have a relatively small amount of data. So for retail products where you have an online catalog, you want to recognize on real shelves, it's a big problem with data. Same holds for industrial objects where you have complex environment and different 3D poses that we need to cope with. Of course, in both cases, it's fine-grained, so many classes which are similar, and you want to distinguish between them besides detecting them in the wild. And seemingly unrelated problem, but still we'll get to it in the talk, of 3D point cloud detection, where you need to detect the presence of a 3D point cloud in the scene and localize it in terms of pose, relative pose within the point cloud. Another interesting application is logos. So for logos, you of course can collect some set of images, to train on and have a large set of logos supported. But I still claim that it's very interesting to do an application like this. So you can mark one new logo, and there are thousands of those, so you can prepare all in advance and then start detecting those logos. By the way, all the images I'm showing where you have some annotations around, it's some systems that we have developed in IBM that are outputting these kind of results. We'll get to some numbers later. So even cooler goal, I would say, is to have an image like this. So you have a bunch of animals, and you, let's say, mark each with the box and say what it is, and then go and detect those objects in the wild. But this is a topic for the next year talk. We are doing, like you see, we are doing something, but this is not part of this talk. Anyway, so in this talk we'll focus on the retail products where you have thousands in the usual supermarket, and all of them are fine-grained. You have, let's say, one image per product in an online catalog, like you go and buy on the web, right? You have this picture on the side, and this is this picture. We want to train on this picture and then get an image like this of a shelf, and then get the objects from the image, and seemingly unrelated, but can be done with the same approach, like I'll explain. 3D point cloud detection and recognition, where you have the 3D point cloud, then you have some images where the point cloud is registered on those images, and the point cloud can be large, and each image showing only a portion of the scene. Sorry. and what you want to do is get a new image, right? Which you haven't seen before, but from the same, let's say, environment, and then automatically register, localize it within the point cloud, and then register the point cloud, all with the same approach. So, in a bird's eye view, our approach is a kind of cascade, a set of steps, where if you look closely, you'll see that, you have the query. Okay, so you have the query image, and then, dense descriptors. You can do the classical descriptors. You can, do the modern descriptors with the neural network, but it doesn't change the meaning of it. Anyway, you see that this pipeline actually is very reminiscent of, what people usually do with modern day detectors. So you have this objectness step where you just detect candidates for objects, object hypotheses. Well, you maybe know it as a region proposal network or something like that. Then you have the classification step, then all sorts of refinement steps, and maybe an additional cascade step of a deep neural network. But all of these are not done in the network. They are done in a generative probabilistic model that we use for this particular type of problem where we have really small data and we can't actually train a network. And I'll show you some small comparison later. So I don't want to, to pour too much details on you, and I'm sorry for this formula. You don't really need to read it. You can go to the paper later if you like. I just wanted to show it for completeness. Let's say that we have something mathematical inside. So the query image is sampled by a dense descriptor. So it could be a classical descriptor, like I said. It could be a neural network which does computes its feature vectors on a certain level. In the regular grid way, as usual, as network does, it slides a window on top of the image, the receptive field. So you have these descriptors, and then all of the descriptors are put in this generative non-parametric model, which is basically a variant of naive Bayes, so generalized half transform, where you have these descriptors here in the blue. So these are the observed variables, and the model is trying to explain all the descriptors we collected, so that it's using these unobserved variables which we are really interested in, which represent the object hypothesis present on the image. So we have the location of the object, the scale of the object, the class, and the camera pose if the object can rigidly transform. We're talking about rigid objects here. The point cloud is rigid, the same as for the retail objects. Well, essentially rigid. They can deform a bit, but it's like we consider it as noise. In addition, we have all these variables here, which actually are here for making it more flexible. Each of those variables allows the model to, at random, disconnect any of the descriptors and say it's generated from the background distribution. It's not important for the model. The model doesn't have to explain it. So these are the variables here. So anyway, I bored you enough, I think. And like I said, we do it, in a cascade, in a iterative fashion, different steps. I'll show you just an illustration. We have this query image. We collected the descriptors. Then first we compute a posterior for the location and the scale. This is the objectness, right? We just want to know where the objects are, but without knowing what they are. It's particularly useful for the fine-grained case, because in retail, you have many, many different variants of the same product. And collecting information from all of the variants together, just to know where the object is much more useful than trying to detect each of them individually, and more efficient as well. So there are some details here on how we do it. We use some sublinear search methods. We are using either KD3 or locality sensitive hashing with some propagation algorithm. I suggest you go to the paper, for more details. I can't really explain all the details here, but just to get you a feel of the thing. Now, having this hypothesis, we can back project. We can go back to the image and say which of the descriptors supported each of the hypotheses, and have a certain segmentation of the scene, let's say. Each segment is supporting a certain hypothesis, and then we can use those, segments to vote for the correct class, and so on and so forth, and then we get the result. In some cases where we have the 3D pose as well, we also regress the pose from those, back-projected descriptors. And finally, we have a post-processing step of a neural network, which is, doesn't add a great deal to the performance, but it's still good for stability. And what's special about it is just besides being a regular classification network, it's also getting the posterior for the class variable over everything we have collected or inferred, and then uses this for refinement. And finally, before I go to some results, how this thing that I just described can be applied to the point cloud application. I'm sorry, this half I'm on this way, but it's because the screen is there. So anyway, in the 3D point cloud application, we can actually see that although this is just an illustration, although the whole image can be transformed projectively when we rotate it in 3D arbitrary way, especially if there is depth inside. Here's just a plane. But I think it's reasonable to assume that locally, all the deformations are basically shift and scale. So if you look locally enough, you'll just see shifting, portions of the scene. And we can use that because we have this detector from before. It's very good at detecting partial matches. So it can actually, with this back projection step and so on, it can actually match the object not in its entirety, but only a small portion of what is visible. So we can use this approach to just detect the images from the construction phase of the point cloud, and after we map them, we get something like this. So we have this query image. And then we can actually use the detector from before, from a large collection of training images for the point cloud. We can match them to this image and then get some partial match, the first hypothesis. Then we have the second hypothesis and the third. And you see each such hypothesis brings us new matches for the point cloud. And it's much more stable than just trying to match individually every point, because here it's a much larger support. After we have all those matches, it's pretty straightforward to compute the PMP and have the pose and map it. So I hope the videos will play. Yeah, 3 minutes and a half. I'm good. It's okay. So here we see some qualitative results. Have the point cloud matching, the products, and of course. This is only some of them. We have quantitative results on established data sets of retail products, which don't look like the ones from the previous slide. They look like this. And so there are a lot of numbers, but we won. That's the last column. And I promised you from before, some comparison to, the established methods. So of course, you can't train faster CNN on one example per class, but you can do something. So in this particular data set with 3,000 product categories, those categories can be, grouped together to 20-something classes, like yogurts, bottles, stuff like that. And then you can try to train faster CNN. You have hundreds of examples per category, so it's kind of okay. But you still see that using this fine-grained and particular method that tries to identify the categories, the right ones, not the general ones. It's much better. So you see the red line, it's our approach, and the blue line, it's a faster CNN train on this. And you have to believe me that synthesis doesn't help here. So we tried to synthesize examples, and it doesn't help. I'm done. Thank you.